Thank you. All right. So yesterday I went on a tirade against everything verbose and indirect. So today we'll talk about my favorite verbose programming technique. And as you know, I hope by now, if you've seen any of my previous talks ever, I have an extreme preference for this brutally simple, concise style of code. But there's a reason that I sort of became this way, and that's because a lot of my programming career has been essentially funded because of people claiming you can't do X with Y. There's a lot of that. That's how I got my first paper published. That's how pretty much everything has happened, is people saying that these things can't be done. And so, of course, me being the contrarian that I am, immediately get nerd sniped and say, I can and I will. But I notice there's an unfortunate, bad nerd sniping habit, is that you say, I can and I will, but then you do it in a way that is useless. It's theoretically possible, it's kind of possible, but nobody cares, nobody's going to use it. So it has to be, at least for my definition, practical. And I'll quantify what practical means. But sometimes you need to try to find something, and it needs to be more than theoretical. It needs to be really, really, really usable within whatever context you're trying to work with. So for me, this means primarily the experience of working with the proposed solution needs to be really compelling. It needs to be useful. It needs to solve the problems that you want to solve. It needs to be technically good, but it also, from the user's perspective, the developer's perspective, I want any solution I come up with to solve a problem to have a good experience and a good design to it. And in a lot of ways, my entire compiler history working on building my codefunds compiler was because there was this gap in the APL understanding. And the assumption was that you don't really do tree manipulation any different in APL than you would anywhere else. You just build this nested structure, and you recurse down it. And I was like, no. We're going to do this better. So a lot of what I did was to figure out how to do tree manipulation in APL naturally, in the way that APLers would say this is APL-ish. And with that, I get to this point where I feel pretty confident saying that for the most part, APL can pretty much have a direct expression of any solution that you have for a problem that is basically solved by traditional computer science algorithms, all your core ideas. The APL can pretty well do it directly. But there was this one gap that was really annoying, and that's event-driven reactive behaviors. And we have a lot of event-driven reactive behaviors these days that we depend on. And specifically, I want to highlight what I mean by an event-driven behavior, specifically by highlighting why I had trouble thinking about an APL solution for this in a way that feels good to an APLer, right? And the first one is that for it to be a reactive event-driven system, you have to have non-deterministic events arriving. And that means you cannot predict how many events you're going to have or when they're going to show up. And you also need to have the requirement to at least sometimes respond immediately. And by immediately here, I mean you have to respond without being able to see any further messages. So that means that all of the typical techniques we do in APL, this batched up work, this collection, this operation over large collections of data, all this batch processing type stuff goes out the window. It doesn't really work when you may get one message and have to do one thing out. You may get 3 messages and then respond or whatever, right? So for me, this has been a bit of an open question for a long time. And I really, really wanted to solve it, so I let it percolate a lot. And one of the problems was that we've done a lot of event-driven programming in APL. All of the commercial legacy APL systems are event-driven systems, or most of them. And so we've done it, but it hasn't been a good solution. And the reason it hasn't been a good solution is because it's basically done the same thing that everybody else has done, and it doesn't meet what I would consider the requirements for my standards of a good APL-ish solution to a problem. So one, any good solution to this would have to have very low overhead. It would have to be inexpensive in various dimensions. It should be low abstraction. It means we shouldn't be building huge towers to do this reactive stuff with lots of runtime support. It needs to be high level and domain-centric. That means we don't want to have to do a lot of translation. We want, in some sense, our stakeholders to be able to work with this code too at some point, right? We want it to be reasonably concise. And this turns out to be a really hard one. So you can tell from the title, I might have given up on that one. It needs to appeal somewhat to the mathematical elements. It needs to have some of the same beneficial properties that we would think of when we think of math, which one of the biggest ones is we need to at least be able to have some way of thinking about the proofs of correctness of this thing. I need to be able to have some idea that what I'm writing is correct. And for me, it's also very important that all of this stuff is pen and paper friendly, which means I need to be able to think about this without too much tool support. I need to be able to just get on a whiteboard and do this, or get on a pen and paper and do this. I shouldn't have this huge tech stack that I need to in order to leverage the technique or the feature. So why do I have these requirements? Because this is a pretty hard set of requirements to put on any programming technique. And it goes back to this idea, which is the idea of APL as a specification language, which encapsulates a lot of the philosophy of use of how I approach developing applications with APL. And so what do I mean by specification language, and how does that inform what we think when we think about APL as a programming language? So if we think back to the core development loop, and no matter whether you're Agile or whatever else you want to call your development model, Scrum, which isn't Agile, you have essentially something that amounts to this flow somewhere in your development process. You have something that defines user requirements, which is turned into something, sometimes an implied specification, which is then implemented and tested, right? Now, you might write the test before the implementation, but you're still writing the implementation and then do the testing. So at the very top, user requirements, they could be user stories, they could be cars, they could be somebody coming in telling you, hey, I need to have this done, right? It's some kind of thing that's in human language that expresses a desired behavior, right? And usually it's informal. That's usually a key feature of the user requirements. Now, a specification is where I'm going to get a little particular here. So I'm going to define the specification here as a formal definition of the user requirements, right? In other words, we're going from an informal, possibly inconsistent, possibly verbose idea into something that can be fully specified and totally defines what your system is supposed to do. So this is specification in the sort of formal software engineering sense. Now, very often people do not write out a formal specification for their code, but they still have one, at least in their heads when they're programming. Or they would like to think that they do. So then, typically, we have programs, and programs typically implement that specification. Now, it is very often that this specification is implied and not formally written out anywhere. So here's a very key point about formal specifications, is they cannot be mechanically verified. Properties of a formal specification can be sometimes mechanically verified or proved using a proof checker or something like this. And some properties can be proved with a type checker if your formal specification is written in a typed language or something like this. But fundamentally, the question of whether or not the formal specification is saying what you want it to say cannot be mechanically verified, because that formal specification is a reification of the user requirements defined in human language. So for instance, you can't mechanically assure that the fact that the formal specification says this should be read is correct, because that's simply a human choice that they made. And this is really important because there's this gap, right? Because in a lot of cases, we tend to ignore this part of the development process. That there's this huge element, which is that only humans can decide a certain level of what is right in a given program. And so if we zoom into this interplay between specification and implementation, we can sort of refine where our existing technology tools fit within this picture. And so typically, you would have your programming language as your implementation language, and somewhere between specifications and that, you would have types of some sort for any definition of types. And maybe they're reified into your source code. Maybe they're sitting in your head somewhere. Maybe they're documented in your schemas of your tables or something. But they're somewhere there. And then on top of that, you have the specification. Because the specification and the types are really not the same. The types only partially implement or describe what the whole specification is describing. And that whole specification has to describe every type of behavior that we are dealing with, at least at some level, right? Which is also including what effects we should see from the implementation. So types are not sufficient to fully specify the program. And so if we insert APL here, what we find is that this isn't a good match. And the reason it's not a good match is this is not how we typically do our APL programs, nor how we want to do them. Instead of going from specification to implementation, APLers very strongly prefer the concept of specification and implementation as the same thing, right? Where the language APL is more like an executable specification of our behavior. And this has a really interesting effect because remember that specifications cannot be mechanically verified, which places a burden on us as APL programmers to ask, can we human verify that we're doing the right thing? Are we saying what we want to say? And we don't have another mechanism that's going to tell us you missed something because we're not relying on a separate formal specification somewhere, usually. So let's look at some existing solutions, compare them, imagine inserting them into an APL context, and see how they work out. And I would generally group event-driven programming into 3 big buckets, right? You've got functional reactive programming, which we put at the top here because everybody's already thinking it. And then you've got callback handlers, which is what I would consider the dominant mainstream assumption of how event-driven stuff is done today. And then event loops over switch statements, which is how everybody used to do it, right? And there's still a lot of event loop over switch statements that are being done everywhere. But it's kind of out of vogue in some sense, right? People have tended to move towards, like in the DOM or in other reactive systems, they tend to go towards callback handlers. Erlang type systems also tend to be kind of callback heavy. And then functional reactive programming attempts to sort of apply some kind of functional wrapper over all of this stuff in the way we think about it. But every single one of these has the exact same problem when we think of them as specification techniques instead of as implementation techniques. And primarily, all of them implicitly or explicitly assume the presence of an understood correct idea of what it is you're trying to implement, right? And in order to guarantee correctness, it's either a formal, like a type verification that's partial correctness checking over some specification, or it's some other form of ad hoc correctness assurance, right? And completeness, the idea that we've covered everything that we want to cover, is entirely ad hoc, right? We get some guarantees, but usually those guarantees are always defined relative to the correct specification. So we don't do anything about specification here. And to make sure that these are all correct, they still fundamentally really, really depend on human verification, but they don't really provide much in the way of techniques to tell you as the human how to verify that you're doing the right thing. They just assume you know. And types don't save us here because types always sort of define that intermediate space, not the full specification space. So you still have to assure yourself at some level that your types are what you want them to be. And then, if you can assure yourself of that, you can get some assistance in implementing implementing the specification. But it only goes so far. So what is the core fears that I have if I'm going to use one of these systems in a complex environment with events and non-determinism and everything flying everywhere, where I have to human verify this stuff? Well, one of the first ones is, have I forgotten something? And the problem is people do not pay attention enough to this question, because systems all the time break down because you forgot an edge case, you forgot this, you forgot that, you didn't cover it, and then systems fall down. And sometimes they fall down really late in production, where you didn't even realize this was going to be an issue until way later. And it's very hard sometimes in the way we do our existing systems to see that we have forgotten something. And I consider this one of the primary ergonomic problems that I want to have addressed if I want an event-driven system in APL. And then, have I done anything silly, right? That's, again, surprisingly easy to do, right? It's surprisingly easy to introduce strange effects in your system that sort of are inconsistent in some way, that create emergent behaviors that you didn't expect to have happen. And are we sure this is the right thing, right? And this, we can get some assistance, but very often we still, is this the right thing, depends on asking a human, is this the right thing? And do we have a way to accurately contextualize that question for the human who needs to make the decision so that they can say, yes, this is why, and this is correct, and this is why it's correct, right? So in some fields with these things, you need some sense of traceability. Why did you make that decision, and where can I find the reasoning, and where does this exist in the code? So off to the fields to look for inspiration to find some solution to this, right? So given that I'm in an APL land, right, it's a math notation. So why don't we see what the mathematicians do? How did they solve this problem when they're just writing papers? So you go around, you look for how people model event systems and the history of this stuff, and oh, what do you discover? They make state machines. Okay, kind of mundane, but okay, sure. And then let's go look at what Iverson did. Did Iverson ever try to answer this question when he was writing APL? Did he ever have to tackle this problem? It turns out, yeah, he's a mathematician. He built a state machine operator in J. So he just made a symbol that said, hey, here's a state machine. Here's how you'd work over it. But I've talked with the J implementers. I've seen that primitive, and over time, we've sort of come to the conclusion that that operator and that interface to state machines doesn't really solve any of the problems that we had, that I described before. And it's kind of complex and clunky, and it's just not very good as an ergonomic solution. So we've kind of, I'm kind of rejecting that particular approach to a state machine for sure. But that's at least 2 votes for state machines in this kind of space. So we're kind of converging on a single solution here, which is never comforting, but you know, it is what it is. So let's consider, does it solve these problems? Just use a state machine. Does it solve this? No, it doesn't, right? It gives us a technique, but it doesn't really compel me that just using a state machine is the answer here. So keep looking around, and oh, look at this thing called Clean Room Software Engineering. They're crazy. I wonder if they've got something interesting to say. And they're famous for having a development process in which your developers are not allowed to have an executable environment in which to run their code. They must only write the code and prove that it is correct. And then somebody else is going to test it and see if it works correctly. And if it fails, they have to go back to the drawing board and ask themselves, root cause analysis, what in your process was wrong that allowed you to introduce this bug into your system? So that's interesting. That's okay. And it turns out, oh, they also use state machines, but they have a specific process for state machines. And they used state machines to do the functional specification of their projects, at least some of them. So that's curious. And what's nice about this is that they specifically frame their specification process as making sure that things are correct, complete, and consistent, which is another way of phrasing all of these worries that we have, right? And so they took the state machine and they developed a specific process of building state machines as users to try to fix the issues of how do we make sure it's correct, complete, and consistent, and how do we make sure that we get these answers in the presence of not having any way of mechanically verifying that this is correct, because our only source of truth is the user or a human language document. And they came up with something called sequence-based enumeration, which at its heart is actually a very simple technique, but I've rarely seen it properly and rigorously applied. And it turns out to be my favorite verbose programming technique. And at its heart, it's a process, and this is important, it's a process for modeling your system behavior by building a correct, consistent, and complete state machine based on a human language requirements document, or something like that. Your user requirements could be a stakeholder, user stories, something like that. But fundamentally, it's that you don't start with already having a mechanically verifiable thing. And so the FRP people would be happy at this point, because they start with the concept of defining system behavior as a referentially transparent function over sequence histories, a stimulus, giving you a response. So the history of every type of thing that you've seen before, coupled with the new thing that you've seen should give you a possibly empty response. So then the question is, if we model our system like this, what are we trying to do? We're trying to find some way to systematically define f. And so sequence enumeration systematically defines this by defining your set of stimuli and your responses, and then systematically enumerating all possible sequence histories. And you look at every single sequence history, and you consider every new stimuli that can come after that sequence history. And you ask, what's the response in this exact situation? And you record that. And then you ask, after we have responded accordingly to this sequence, is there another sequence that we have seen before, or in other words, that is smaller than what we are now, for which we will behave equivalently moving forward into the future? So in other words, is there an equivalent sequence that's shorter than we are, that accurately matches all of our behavior into the future? That's called an equivalent sequence. And if there is no equivalent sequence, then we know that that sequence plus stimuli that we found is called a canonical sequence. It represents a new state in our machine, and so we define it as a new state in our machine, and we go from there. And then we repeat this process. So the recognition of equivalent sequences is how they bound the exploration process. It prevents us from going into this combinatorial explosion because we revert back to previous sequences that we've already seen. And this process, because it's systematic, means that we have defined the state machine in an extremely careful way rather than in an ad hoc way. So I'm going to use the Clean Room Book's demo version of this, the security alarm, to illustrate this because I think it's a really good, straightforward example. So they define a security alarm. And you don't get a more simple event system than this. You can set the alarm. You have to type in a 3-digit code to disable the alarm. And the alarm can be tripped by a tripwire. And if you mess up and type in a bad digit, you can hit clear to reset and try again. But another thing is that you're not supposed to know if you've typed in a bad digit. So it doesn't tell you. So let's actually look at how this would look if we took it from a specification and we made this an APL executable specification. So here's the APL session. And, oh, I'm going to have to type with my neck craned. Let's see if that works. Let's see if that works. OK. So I have some variables already defined and some functions. We're going to go take a look at these, right? But let's start with our system requirements, right? So we're going to look at our system requirements. So this is the system requirements that are, and I just enumerated them. That's what that funny squiggly stuff at the beginning was for. I just wanted to put numbers on this end. So we start with a set of system requirements. And then we have to think, what are our stimuli going to be? And so if we look at our stimuli, and if you, so we've represented this set as a vector of character vectors. So you can have a set event, a trip event. And here you can see where the specification stuff starts to take place, is we abstract the digits, and we just say, have we had a bad digit or a good digit? And then we have that clear event. And so if we're going to turn this into an executable thing, I like to have a set of enums for each of these. So these are just enums that map this same set into numbers starting at 1 and incrementing by 1. And that is important. We'll get back to that one. And then we have a set of responses. So alarm off, alarm on, light off, and light on. And each of these is just a function, a null. What null? Did somebody say we got a null? OK. Sorry, I'm hearing things. The ghosts of APL past. So each of these functions for us is just a single nillatic function, or you can think of it as a a nullary function. It takes no arguments. And all it's going to do is these are just going to print out the event that's occurred. So if I say alarm on, it's just going to print alarm on, et cetera, right? So we've defined our stimuli, and we've defined our responses. So now, what we can do is we can define our spec. Now, we don't have time to sit here and do the enumeration ourselves here, so we're not going to do that. However, I will at least show you the code. And so you can see each of these is one of our enumeration sets. Let's see, do I have a laser? Ooh, interesting. Weird. All right, I've been nerd sniped. OK. So is there a laser pointer on it? It's a trigger? What the? Holy moly. We're putting that down. That's a dangerous weapon. I am not qualified or trained on such devices. So this spec is another one of these nullary functions. And we have labels on the left-hand side. So each of these is a label. And this is our empty set. So we've seen nothing so far. And what we're going to do is we're going to listen for events. And our listen function is going to return one of our events that we see. And where it gets funky is that arrow there, that means goto. So what you're seeing here is a computed goto, which is going to jump to one of these lines here. So remember that our enums were 1, 2, 3, 4, and 5. So all we're doing is computing an offset to jump to the next statement. So this is just an old school switch statement at some level, but in a way that models the table for a specification that we want. And then we're going to do any response that we want. So when we get the set, the light is going to turn on to indicate that the alarm is set. And then we think, is there an equivalent sequence for after the alarm is set? No. So then we are going to go to that new state, which is we have seen the set event. And so that is our next state. And the ... is my way of indicating that all of these other events are illegal here. They shouldn't show. We should never get one. If we get one, this is like a big system crash because something about how we understand the system has gone horribly wrong. So if we've already seen the set, what do we do next? And you can see this pattern. If we see a set and another set, it doesn't matter. We can hit set as much as we want and nothing's going to happen. And so we're going to return back to the same state after that. And you can see the pattern here. We just continue on this exact same process. If the alarm is set and we see a signal from the tripwire, then we turn the alarm on. The alarm goes off. And then now that the alarm is on, we're going to behave differently. So we have a new state to handle that new situation that we're in. And so on down the line. And so then we account. Now this example is trying to show that enumeration space. So instead of abstracting all the good digits, they actually track how many good digits you've typed in. So once you've typed in 3 good digits, that means you've entered the correct password, and you can turn the light off. Right? You've disabled the alarm now. And if the alarm had been tripped, and you enter 3 good digits, now you turn the alarm off as well as turning the light off. And then you're right back to square one at the end. So now's a good time to ask, does this process seem obvious to everybody, or does anybody have any questions about what we are seeing here? Yes? And I'm going to show this running, so we'll execute it and play with it. But I like to go abstract first and then execute.
Sure.
Before, so.
I'm just wondering about, wouldn't this explode in complexity if you add more cases and?
Yes. So it's a good question. One of the ways in which we manage the complexity is looking at equivalent sequence states. The other is something called stimuli abstraction. So I'll talk about that at the end. But remind me if I don't, because that is a key element of this technique.
Sure,
so,
thanks.
Yeah. So what we can do is, let me show you what listen does. So all listen is doing is it's listening for we're going to just type in one of our stimuli that we receive. It's going to look that stimuli up, and it's going to choose the correct offset and calculate the computed offset from the current line count that we're at, or line counter. And so if we hit spec here, it's just going to wait for something. And I've said, if I don't type anything, I'm going to exit. But I can type set, and it's going to say, oh, light on, because we saw the set situation. And I can trip, and now the alarm's on. And, oh, well, I can type a bad digit to try to disable it. It's not going to tell me anything, right? It's not going to give me anything. But if I then clear that, and I type in a good digit, and I do that again and again, then it's going to turn all the alarm off. But then to rearm the alarm, I'll have to hit set again. And you can see this as we go through. We are enabling and disabling the states, and it's just a state machine, right? But this is a really simple way to manage that event-driven system, right? And now, what's interesting about this, from the clean room people, they also took this a step further, right? Because this spec often in a system, so they used this specification technique for everything, right? Your entire system was specified using this system, and then the whole system was implemented from this. Where I'm taking it is with APL, the APL language is a better specification language for most problems. So I reserve this technique just for the correct specification of the event system itself. So I very strictly constrain the event space. And so that also, to answer, sorry, I've forgotten your name. Sorry? Theodore. Yeah, Theo. Okay, Theo. I can work with Theo. So to answer Theo's question about state explosion, one of the ways I make this a lot easier is I don't try to specify the whole system. So I have used this technique to specify large systems. So the parser for this, I did specify it, and I tried specifying it pretty brutally, and I think I got up to like 300 or 400 pages. And it was very useful because I actually found a lot of bugs through this specification process and unique, strange things that I had never considered in the parser. So it did its job, right? I found all sorts of things about parsing APL that I had no idea about. But that's a very verbose way to go about it. So if I restrict this technique to just event-driven programming inside the ASPL system, that already constrains the level of events that I have to handle. But the clean room people, because this was their primary specification method for the entire system, one of the things they also needed to do was generate stochastic black box tests to certify that the system was correct. Well, what do they have here? They've got a state machine. So what can we do? Well, what are the canonical sequences in this system? So these are the canonical sequences. There are 9 of them. So what they did is they said, let's build a usage model off of our functional specification. So I've gone ahead and done that. And this gives us weights for probabilities that any given transition is going to occur within this state machine, right? This is like a little Markov chain type thing, right? So now what can we do with this? Well, we can now generate a test case for this, right? So I can go and generate a random test case off of my spec along with what I expect to happen, right? And so I built a fuzz tester here that's derived exactly off of the specification that I'm working with. And so how do I do that? Essentially, I redefine all of those stimuli and responses. And then I run the spec. So I'm running the exact same spec code, but this time I've changed all my responses to add my response to a response set. And I've changed my listener to go in, figure out what the canonical state that we're at is, right? Compute the weights over that canonical, look up the weights for that canonical state, and then just randomly pick one of those edges based on the distribution of those weights. So you might not understand the APL code, but does the concept of what we just did make sense? Now I'm happy, we've got a little bit of time, so we can talk about more of this. We can go into more details I can explain how all of this code works in detail, or we can theorize and philosophize and questionize. So up to you guys. Would you like to see some more of the code, or okay? So we can break this code down a little bit. Let's look at the test generator. Let's go in and let's debug into this space, right? So we're going to go through this a little bit, and then we're going to run our spec. So let's go into our spec and watch our spec run. So here we are at the first space. So we go in here, and now we're going into our listen function. And if we look into our listen function, we will see, this is too much code. I don't like giving my mouse. All right, that's better. Okay, so if we look in here, we've got LC defined as 1. So in other words, we're at line 1 of our spec. And we are generating a length of 5, so our length is still 5. We're all good there. So now let's think about our state. How are we going to extract out what our canonical state is? Well, we have something called reflection in our system. So I can look at the source code of the spec file, spec function, and I can extract out the line that I'm on. So let's look at that line count from that specification. So I'm on that line right now in my program. So now because this is a demo, I happen to know that the line count that I want to cut off is this stuff, right? So what I'm going to do is I'm going to search for that inside of that string, and then I'm going to take only, whoops, there we go. And so what I'm basically going to do is just take everything before that colon. And that gives me my canonical sequence that I'm at right now. And I don't want that underscore, so I'm going to drop that off as well, right? And that gives me my state. So I can run that. And now my state is that canonical state. So now I figured out what my canonical state is. So now how do I compute my weights? So I'm going to go in here, and I have my set of canonical sequences, right? So then I'm going to go in there, and I'm going to ask, which canonical sequence am I? Well, I'm the first canonical sequence in this case. So then I'm just going to say, well, in my usage model, what are my weights? So in this case, my weights are all 1 and 0. So I only have one option here, right? So that gives me my weights. So now weights has that value. So now, how do I compute the distribution on this, right? That's this next line. So I have this ability. I can produce a random floating point integer from 0 to 1, right? And here's where the fun comes in. Let's take some sample weights like 2. Let's assume we're evenly distributed across all of the sets. So I can produce something like this. This would be an even distribution. All stimuli are equally possible, right? So if I scan over so scan over the 5 row of 0.2, I get the accumulating running sum of those values, right? And so this forms a sort of interval that divides up or slices up the range from 0 to 1, right? So now I have a function. So we have, let's say 0, 10, 20. I have a function called interval index, where I can give myself a number, and it will tell me the index of those intervals that I belong to, right? This is a binary search. And so I actually 7 belongs in this interval, which is indexed by this first piece, right? So this scan here is providing that same interval just on 0 to 1. And so then I can use interval index on that random value and get one of those distributions, right? Now, I could get -1 here, and so I don't want that. I actually want to get something above. I want to shift that up to 1. I don't want 0 or -1. So I end up taking this result, and I have to do a 2+ on that, right? And once I do that, I can store that into my if you look down here, I add 2 to that, and then I store that. I add that, concatenate it to my set of sequences that I've seen, and then add the line count to it to compute my new offset that I'm going to go to. So I can just run that. And now my offset has been computed, and I'm going to do this. I'm going to execute this line. And so you can see I've jumped to this. And if we look at the S and R values, you can see we've already seen one event sequence and the light on. And then things will just repeat this over and over and over again. Right? And so this is quite a simple thing that we have, but it solves all of our problems that we have with our requirements. So if we think about this, this gets to your question, right? This whole process is pretty straightforward in the trivial cases. But what happens when you start getting this strange explosion? Now you have to make decisions about how you're going to think about your problem. And there are 2 primary things you have to think about. What are our responses that we actually care about? And what are the stimuli that we actually care about? So for instance, they already did something called stimuli abstraction in that spec. Rather than tracking every digit, 0, 1, 2, 3, or whatever, which would have caused way more state explosion, they collapsed it to the core idea that their domain actually cares about. And this is where the domain centricity comes in, is they actually just cared about, have you typed in a bad or a good digit, right? So you can do the same thing. You abstract your specification to work over these abstract stimuli rather than the raw events that you see in your system. Now the rule is, if you are going to do that, you must be able to prove, fundamentally, a formal definition between the sequence history that you're accumulating and the abstract event. So you must have a formally defined function or expression or specification that says, this set of sequences that are the raw sequences formally map to this abstract stimuli. And this is how they do it, and this is correct. So you have to verify that that abstraction is correct. But by doing that, you greatly reduce your state space that you have to explore. And so for instance, as we will see in the workshop at the end of this conference, one of the examples we have there has an example where simply by introducing one additional stimuli, and no additional state, right? So this is important, as I tend not to want to introduce additional state into the system just for tracking. If it's control flow tracking, you might as well have it in the states themselves. But if there's other state in your system, like global application state that already gives you the information that would have been in the state system, you can abstract that into your stimuli. So in one of the examples we've got in the workshop that we're going to go over, we collapse a 4-state system into a 1-state system simply by adding one more stimuli. Right? And it's those kinds of techniques that make this scalable, right? Does that answer the question? Yeah. So the reason this is different than something else is we are specifically focused on the process of state exploration and how to make that a tractable problem, right? That's what makes this different than other ones. This is the key emphasis in this technique, and you can apply this in other ways, but this particular approach makes it really ergonomic to do this. And because we have a state per line in the way we've expressed this syntax, we now can put a comment saying, this exact user requirement is why we're making this decision. So we have the ability to do regulatory traceability all the way back to the original decision makers. And if we have to invent new ideas, we can record why that idea was put in and have augmented user requirements that were technical requirements that were discovered in the course of doing this specification. And that can very much help under certain environments where you are heavily regulated or where you need to prove that the decisions you made are valid, right? Another thing that you can do with this whole system is because you've got a state machine now that is so regularly expressed in your program, you can extract out a state machine expressed in any other language, and namely TLA+. You can now map a TLA+ or put it into some other model checker, and now you can do proofs over that state machine about things like deadlock and progress and resource contention or any of these other issues that can come up. So if you've got a protocol that you're working with across your systems that are communicating over these 2 states, you can now take your code and verify that the actual code itself is correct and deadlock-free with respect to that abstraction level that you're working in. And that's a really powerful technique, and it doesn't obscure any of the rest of the stack, which is very important to me. I can lift into that, work in it, but I work off the code instead of somehow trying to develop the formalism and then implement the code. I want that specification and implementation to be the same thing. And it really is primarily for me about making sure that we have considered every possible case and had to make explicit decisions. You can make the wrong decision, but at least you've had to confront it. And you can't pretend like you didn't have to think about that at some point. And this greatly reduces or eliminates unexpected behavior, more or less. And so you can use model checkers, prove temporal properties, all sorts of great stuff. And of course, if we go back to that requirements list that we had at the beginning, well, we have extremely low overhead, low abstraction. It's very flexible. This whole technique can be leveraged, and we've used essentially no programming languages features, right? We're really low level. So this means that like a compiler can take this and compile this down to extremely efficient code under the hood. There's no abstractions to worry about. And interpreters can do this very efficiently. Like all sorts of things can do this efficiently. And so like at the workshop, these are two applications we're designing that are built on this same technique, right? This little Galaga app and this spreadsheet application over here. And you can see all of the elements here are reactive to this thing. Both of these are done on a web platform. One of them is done with a rendering loop that keeps up a reasonable frame rate, and then the other one is done using DOM manipulation. And so we've got two examples of how we're going to do that in the workshop. So if you want to write these programs, come to the workshop. So anyways, in conclusion, sequence-based enumeration can be used as a foundation for defining an executable specification of event-driven behavior in APL. And it's not perfect, but it's way better than anything else I've got. So it's my favorite. Thanks. And I think we've got time, right?
Yep, we have a few minutes.
Excellent. If anybody's got any other questions.
There's a break at 3 o'clock, so we don't really run into anything else.
Okay, sure. So if anybody's got questions, yes.
If two different sequences lead to the same state,
Yeah, so if you've got two sequences, in fact, there are infinite number of sequences that map to the same canonical state, right? So at some point as you're going along, you might discover you've got this longer sequence that you behaved differently up to this point, but now you're going to behave exactly the same as some other sequence you got. We call those equivalent sequences, and those just go back to the original canonical sequence, which is the shortest of those.
If they're two of the same length,
you just pick one. Yeah, you usually define an ordering, and the ordering, you define your lexicographical ordering, whatever it is, and you just pick the one that's lexicographically first. Yeah.
Question
Yes.
question about when you were taking in input on the keypad, and there were certain right numbers, and then you specified, we can reduce the total amount of options we can give in here to right numbers or wrong numbers.
Right.
Is that kind of like a tagged union type, or I don't know why my brain went there, but it seems like it's a way where we're grouping.
No.
Okay, because
So
I don't know types.
I am sure somebody could prove mathematical isomorphism to that, but I, as a thinking habit, don't. What's better to think about it is an abstract stimuli is a stimuli which is a pure function over your logical application state and the sequence history. So, or more technically, you can eliminate the application logic and say it is a pure function over the sequence history. And all it's doing is allowing you not to have multiple states to track an answer to that same sequence history. So an example of this is you might have a multi-user system that needs to log in, and you can only do a bunch of things after you have logged in. And there are a bunch of users that some are logged in, some aren't logged in. You'll see these requests that come in. You don't want to have a state per user. That's ridiculous, right? What you really care about is, has a user executed a valid command post-login, right? So the sequence that you're talking about is user login has occurred already somewhere in the past, and now this command is a valid thing to see after that state has occurred. But rather than having a state that tracks that, you can wrap that into an abstract stimuli so you don't have to record that state, that sequence stimuli in the actual space. Now sometimes, for instance, in a GUI, you could theoretically do that, but you're introducing a state variable somewhere that's purely control flow state. And generally, you wouldn't do that. So like a pop-up window. You might want to pop a window up and down, but there's no reason to store I'm popped up, I'm popped down in your application state. You can store that in the state machine. I'm in this state of the UI, and that's often a better place to put it because you'll have so it's a design question about where do you abstract, where do you express the state, and it's about making sure that the state machine reveals the important questions you want at the resolution you want for your domain and without undue burden, basically. Yeah.
So at first blush to me, it seems like this process of building the state machine would be sensitive to both false positives and false negatives in that equivalence check that the human has to do between the different states. Mm-hmm. Is that something that comes up particularly in larger state machines? And if so, what are some techniques you can do to prevent those? Yeah, so I would say the easiest way is you are somewhat conservative to assuming canonical equivalence, right? So if you default to making a new state instead of reverting to a sequence state, you can then build that state out, look at it, and see if it's in fact similar to something else that you've done, right? And that over time, that will start to reveal itself. So in this process, you get a couple of states in at any given point, and it very quickly becomes obvious, oh, wait, this is exactly the same as what we just did back here, right? Now, of course, you can use analyzers because it's just a state machine. You can lift this up and do, you can write analyzers to say, hey, this state is duplicate to this state. And you can also, again, lift it up and say, hey, this property you think exists in your system doesn't actually exist because you've collapsed two states to something that shouldn't matter. Now, where that false equivalence can also get caught is you can look over your user requirements, and very often there will be a behavior that has disappeared in your system because you collapsed a state, and now that particular behavior no longer emerges in the spec. You can't find that behavior in the spec. And if you can't find the behavior you said existed in the spec and you can't explain why, that's probably a sign that you misspecified something. So you can leverage the user requirements to see how complete it is, because there should be a reference somewhere or a way to demonstrate that all your user requirements are met. And you should be able to verify that by going through it. Now, again, this is all at the specification level, so a lot of this is human, right? But I'm asserting essentially that human is the best we've got here. And when you've got the best you have, make it at least as rigorous as possible to try to do that exploration. So you really stepwise refine the whole thing. It is a danger, but you've got to be aware of it. But a lot of that is judgment, experience, and disciplined practice over the process, and not jumping to conclusions, that kind of stuff. So,
yeah. A solution like this seems to imply that you need to have a coherent system in a way, and usually you. When you inherit some code, for example, and now you're trying to make sense of the code in itself, and is there a way that you could pragmatically introduce this concept into exploration and understanding of what you're doing?
It's a very good question because a lot of people suffer from this. I actually suffered from this, and this is the first success I had with this technique. There is no formal specification for the APL language as a notation. There's just the reference implementation, which literally doesn't build an AST, only does token interpretation over live programs. So I literally had no possible way of extracting the parse information that I wanted to compare of whether or not I was parsing anything correctly. So it was a system that was almost unintrospectable. So what I did is, the reason I did that big enumeration is I started with the inputs into the system, which you always can tell what your inputs into the system are. You can model that somehow. So I picked a set of inputs, and I started enumerating them and comparing what I got out from the system. And that allowed me to start building a formal map of the behavior of the system from an external space. So I used enumeration as a technique to sort of build a formal spec off of and execute a reference implementation. And that, what that often will do is that will point exactly at the incoherent parts of the system. You will very quickly discover this does something absolutely bonkers right here. If you do this, this, and this, all of a sudden we crash here or we blow up here or something. And we encountered some of that in the interpreter because we had hit cases that people had never thought about. and it blew up, or it gave a weird syntax error, or caused a side effect that we didn't expect, something like that. So you can like sort of extract your stimuli and responses, and then begin building that machine and comparing what you see against the actual system. And that helps you to build up your stuff. And then that can be a tool to drive whatever you're doing next. Yeah.
Do you consider behavior trees as another architecture in comparison to state machines?
Behavior trees.
Yes. I know they're used normally in AI for gaming engines and for robotics. And
You're talking about like operational decision tree type stuff.
Yes.
Like symbolic AI, traditional AI stuff. I didn't seriously consider it. I think partly because I don't feel like a tree model is there's a lot of overlap between technically there's a lot of overlap between the executable paths that a state machine describes and a tree decision path. They're very similar in a lot of ways. I think the tree representation model, I never found it very ergonomic. Useful if you don't have to see it, right? But reasoning about it, I think it was harder to reason because the subtrees are more hidden. So like in a state machine like this, I can like move states around a lot more. So it's a little bit easier for me to, because everything's more at the top level, and I prefer working that way. With decision trees, I tend to find that like little decisions here might percolate, or like you have to think across trees sometimes. And so I could easily be proven wrong that that's another way to really explore the space systematically that's nicer. I didn't like how much it hid compared to other stuff.
It's just space because in the end, in theory, they simplified, and then when you scale up, this should be having better performance than a state machine that can explode with the complexity of having too many states. But yeah.
Yeah. The execution performance of the state machine is really good. Yeah. But the exploration state space should be very equivalent between the state machine and the decision trees. Yeah.
I think we're run out of time. Yes. So thank you very much, Aaron, for everything.
Thanks.